Hello, my name is Javier Rodriguez and welcome to lab number 5, Effects of Air Resistance on Different Masses. This lab is loosely based on our second lab in Physics 2211 in Georgia Tech. The main point of the experiment is to observe and analyze the motion of an everyday object that's falling from a measured height. After actually measuring this object and taking a video of it and putting it into Tracker, we'll utilize Newton's second law to predict the motion of the object over very small time intervals. Newton's second law, as you all know, is final velocity equals net force divided by mass times the change in time, and then we add that to the initial velocity. From that formula, we can actually derive the formula for position, which is the final position is equal to the initial position plus the velocity times delta t, or change in time. We can do this because we know that acceleration is actually equal to the net force divided by the mass, or that delta v over delta t, because acceleration is the result of a force acting on an object. And it is also inversely proportional to mass, which is, as you'll see later on, is actually a very important part of our experiment. The second part of the experiment is to actually model this data using BPython. This better approximates the effect of drag with gravity, and we can see how the different objects and with the different masses will fall and how gravity will affect each of them. We should also analyze the object's motion in a situation where both gravity and drag forces affect an object, not just gravity or not just drag force. It's important to determine if the object ever reaches terminal velocity when it falls. So our final results are that after using and analyzing the two models created for this experiment, as in one for 5 frisbees and one for 25 frisbees, we can say that Earth creates a drag force that acts opposite to the direction of gravity force. The terminal velocity is reached when both of the forces are in equal magnitude, as in the force of gravity and the force of drag, and that the 25 frisbee stack takes less time to reach the ground than the 25 frisbee stack. As you'll see later on, the model and the final results had some errors, however, as you'll see when compared to the actual observed data obtained from Tracker. So here's some starting information before we get on with the experiment. 2 sets of items were dropped at the same height. The first set was 5 small and thin frisbees, almost the size of the plate. The second set was a set of 25 small and thin frisbees. So now the radius of these plates is 0.9 meters, and the weight of a single frisbee was 0.0095 kilograms. Obviously, knowing this, we can get the weight of 5 frisbees and the weight of 25 frisbees by multiplying by 5 and 25 respectively. Now, the forces affecting the object are the force of drag and Earth's gravity. The force of drag actually acts in a direction opposite to gravity, as in facing away from the center of the Earth. It's calculated using the object's falling velocity. The formula for it is -1/2 divided by Cp times A times the velocity squared times v hat, which accounts for direction and velocity, because velocity is a vector. Now, each of these things here are described, where P is the air density, C is the coefficient of drag force, which is obtained from NASA, A is the area of the frisbee, which I calculated using a ruler and the frisbee, and V is the velocity, which I was able to obtain from Tracker. The other force at hand is Earth's gravity, which is 9.8 meters divided by seconds squared. It is a force of attraction between the Earth and the object, and it is pointing downwards towards the Earth. Now, here we have some calculations for terminal velocity, which, as I mentioned beforehand, is a very important component of our experiment. Recall that terminal velocity is when the magnitudes of forces of the drag and gravity are equal. This means that F net will equal 0 because the forces actually act in opposite directions. Now, if we utilize the formulas from the previous slides, we found out that 5 frisbees have actually a velocity that is square root of 5 less than the actual velocity of the 25 frisbees, meaning the 25 frisbees fell much faster than the 5 frisbees, and as a result, they reached the ground quicker than the 5 frisbees. Now, if we go to our BPython code, as you can see here we have our initial conditions. We have the masses of both our frisbees, of the 5 frisbees here, the light one, and the 25 frisbees here, which is 0.25 grams. And we also have the initial position and initial velocity since it started at rest. Using all this, and we have the gravity here, all the key components of our formula, we have the time step, and we also have the direction of our object. As I mentioned beforehand, we also calculated the area of the frisbee. We found C. I found C from NASA, and we also found P, which is the air density. Now we actually get into the loop, where we keep updating the position of the objects and the velocity that they have. Here is the force of drag affecting the 5 frisbees in their initial step, and here's the force of drag affecting the 25 frisbees. Gravity is also a key component here, since it's the other force acting on it, and it's actually negative because it's acting in the opposite direction to drag. We also have the net force here, which is Newton's second law applied into code. And since this is looping right here, we also get the new positions of it and the new velocities of the objects every time we loop, until the loop ends. And finally, these few lines right here are just to draw the arrows that you'll see when I run this code, say where the force of drag is aiming and where the force of gravity is aiming, and their respective magnitudes. Let's run the code now. So here on the left, the blue ball is actually the 5 frisbees, while the red ball is actually the 25 frisbees. And as you can see, the 25 frisbees actually have a much bigger force of gravity here because they have a bigger mass. What this means is that the actual object is falling much faster than the 5 discs, and as a result, the force of drag is less. It's more on the red ball or 25 discs or 25 frisbees, but since the difference between it and the force of gravity is so big, it will still fall faster than the actual 5 frisbees. Now let's go back to our presentation. As you can see here, here's the actual video from Tracker. The objects were dropped from the exact same height, which is right here, from a person standing atop a chair. On the left side we have the 5 plates, and on the right side we have the 25 plates. Now here we can observe our final results. In this graph you can see both the model results and the actual observational results. Both of these right here are for our 5 disc. As you can see, the pink one is actually very similar to the blue one, which is the model one. However, at the end, the object is actually falling a bit faster, and it has a different position than the model one. Same applies here to the 25 frisbees, where the 25 frisbees actually reaches position much quicker, which means that we probably had an error when calculating our position data from Tracker, because the 25 frisbees are supposed to reach the ground much faster than the 5 frisbees. This can actually be seen from our conclusion. So, as I mentioned beforehand, Earth's air creates a turbulent force of opposite to the direction of gravity. This is why the model that only accounts for the force of gravity doesn't produce accurate results. Terminal velocity is obtained when gravity and the drag force are equal in magnitude. The velocity of the 5 frisbee stack predicted was 277 seconds, as obtained from Tracker. The velocity of the 25 frisbee stack predicted was actually 124.5 seconds. However, when taking the actual velocity from our Tracker video, which is the green line I showed in the previous slide, right, which is the yellow line shown in the previous slide, we see that the actual velocity is 124 seconds. So, using the formula for percentage error, we'll see that we have a 0.4 percentage error from our model and our predicted data for the final velocity of the plates, and the reason they reach the ground sooner or later. So these errors may be due to inaccurate measurements of drag forces, imprecision when using Tracker, and movement in the X and Z direction of the graph. Now, I hope you guys learned something about drag force and falling objects, and I hope you have a great day. Thank you for your time.